So the easiest way to deal with this is to essentially use in the function, in the respective function that you're using, like the mean function, there is an option, and this option will basically tell the function how to deal with missing values. And that's important to keep in mind, because that's the way how you can still employ the function without losing that case. So here, for example, it did compute that mean age, but if there were a missing value in there, it would give you an error. So one way how you can look at all these different functions is by question mark and the name of the function. That gives you basically here an overview from the documentation. And here you see already that function. So na.rm equals true. This will basically is a logic value indicating whether NA values should be stripped before the computation proceeds. And that NA.rm equals true works for, I'd say, like 60% of all functions. So that is a super important way to deal with that. It is different. So there's a second one, there's NA.omit. Then it drops the entire case altogether from the computation, which is when you do multivariable models, it's two different ways, whether you just remove it from one variable or you omit it altogether from the model. But more about that later. So this is how you would deal with that in the graded lab. So those of you that had issues, that's the simplest way to deal with this. Good. Any further questions on the graded lab? Well, I think it was somewhat doable, I hope. So today is graded lab 2, and graded lab 2 we're going to do the same approach. So we're going to do one variable first. We're going to deal with that. We're going to analyze that, and then we will. So the graded lab is then up to you with a different variable, but it follows the same outline. So it makes it comprehensible and easy for you. Good. Okay, so we're continuing today with point estimates, confidence levels, p-values, and hypothesis testing, part 2 of hypothesis testing. We are reviewing today what confidence intervals are. We will talk about hypothesis testing and how confidence intervals fit into hypothesis testing. We test hypotheses about population means and population proportions. We write null and alternative hypotheses. We calculate the test statistics and p-value. We do one-sided and two-sided set tests and t-tests for one sample. We're also going to do t-tests for both samples. That is topic 8. So today you're walking out and you will be able to compare two different cohorts. And this is in the end of the day, this is what you will be doing in randomized controlled trials. Because in a randomized controlled trial, you have a participant in the simplest analytic approach. You have a participant enter the trial in either arm. So you have two arms marching forward, and you follow these over time. These individuals will show differences from baseline and from study start to the end of the follow-up period. And these changes you will then calculate, and you have then changes for the control group and changes for the intervention group. And you will then compare the changes between both arms. And this is in the simplest format. You could do this with a t-test or with a set test. A t-test, essentially. T-test with an independent samples t-test where you have two independent groups. So that's the simplest analytic approach to such a design. So you understand already basically how important that is and how important that test is. Also, in the context of the final project, it will be equally important, because you may have an hypothesis with, I don't know, if I have a cohort that is diabetic and a cohort that is non-diabetic, are there differences in blood pressures? It can be a test as simple as that, and you can do this with t-tests. Good. Then we will briefly talk about type 1 and type 2 error and statistical power, and that will basically set the stage for next class, where we'll talk a bit more about power. And this is something that is also for clinical trials extremely important. But hypothesis testing is the basis for the understanding of type 1 and type 2 error and the statistical power. So, okay, confidence intervals. So from last time, remember, confidence intervals is basically an estimate based on the distribution of your sample, in which you are to a certain level confident that your population mean should be located in. So this interval basically gives you an idea. If your confidence interval does not contain this mean of the population, in case the mean is given of the population, then you can say that the distribution you're looking at in your sample is a distribution that is inherently and significantly different from the population distribution. And that's a powerful insight. And that gives you kind of an idea about the representativeness of your sample. So the estimated confidence interval provides a range of population means that are consistent with the sample. Also important to keep in mind, it's actually you're not looking at an actual distribution of individual scores. You look at a distribution of sample means. So based on your one sample mean, you assume with the estimate of the variability that you have from your sample, you assume that all means that you will draw from this virtual hypothetical population will have a distribution around that mean that corresponds with the standard error of the mean. That again is associated and basically linearly related to the standard deviation divided by the square root of the n. So the sample size and the standard deviation basically build the standard error of the mean, which is an estimate of the variability of those means that you have drawn.
So if the sample does not contain, it is very different, like invariantly different from the population, it does not reflect the actual population, because whatever we have on the sample does it reflect on the population.
So if the standard error of the mean and the confidence intervals of the sample, it is exactly, so that's the representativeness, right? So if you have a sample that gives you a 95% confidence intervals, which is different from your set test, you can say this is significantly different. So then you reject the null hypothesis that sample mean and population mean are identical. So then you know you have a biased sample. So it's different from what the population looks like.
We still have to report. We have to report like
that. You would report like that. I'm not sure. What do you mean?
Like, let's say we did an experiment and we have to compare the statistic of it, and it's kind of invariably different. We have to continue the reporting, or we have to. You would still report it, because what it essentially means. Should we turn off the light? I'm just wondering, but it's too light to see the screen. So your sample still shows the dynamic you are studying, right? So if you recruit individuals for a randomized controlled trial, there's actually a really good chance your sample for that RCT is not representative to the population. That's actually a very high chance. So essentially, there are studies out there, and I think I've mentioned this in an earlier class. There are studies out there that studied the population demographics of randomized controlled trial with that of the Medicare population. And they actually found that all these RCTs that are in earlier stage, pre-market availability of the trial, of the drug, for example, are actually not representative of the Medicare population. So basically you're studying dynamics in a population that is not necessarily the population that later on will get it. But you assume that it's still valid to be used in that population too. So if it lowers blood pressure in a population that is 20 years younger than the average population of the Medicare population, why would it not lower the blood pressure in the Medicare population? But these are insights then that are coming from real world evidence. And that's pretty much, that's more of the work that I'm doing. This real world evidence is basically, so you have data from whatever source,
and you are investigating whether a certain intervention was indeed as effective as RCTs have suggested they are. So that's pretty much what this is going in real-world evidence and post-market evaluations as well. So when you think of the different phases a drug, for example, undergoes until it actually gets out on the market, these different FDA phases. So there's the last phase, phase 4, is a post-market evaluation. So basically you are compiling this data that you get from different sources, and you actually look whether the drug was actually really delivering what it was promised to deliver. So that's the post-market evaluation, and that's super important to understand. But yeah, so you would still move forward with RCT participants that are creating bias sample, because you still want to study them. You still want to study your drug, right? And you can, to some extent, you can account for this with replication selection bias, which would essentially be the technical term for it. Is hard to counteract. You can't really counteract it, but what you can do with replication by repeating trials in different populations, you can kind of still have solid inferences to the trial, to the effectiveness of the intervention, irrespective of biases. But good question, thank you. Yeah, so the margin of error, so we talked about this. So this is basically calculated by the sample mean X bar with T alpha half. Alpha is the type 1 error. So the type 1 error, and we will talk about this, is basically where you rejected something that you shouldn't reject. That's the quote unquote p-value. So the p-value that we will be computing today in t-tests essentially is a representation of the rest risk of a type 1 error, with 5% being the most commonly accepted threshold in scientific methods. So 95% CIs are subsequently and consequently the most commonly used confidence intervals. So yeah, so for an alpha of 0.05, we have 207 with a degree of freedom of 22. An alpha of 0.5 would be 0.69. Yeah, the 0.5. 0.5. Why is he outlining 0.5? Yeah, 0.5 is not necessarily one that. So basically, what you would be looking for is an alpha of 0.5. So the way you're interpreting this T table is basically you're first deciding whether it's a one-tailed test or a two-tailed test. Once you know that, you go along and you find the right column that corresponds with that alpha level that you're comfortable with and that you want to embrace for your study. So if let's say you are going for a 5% alpha, you follow the column all the way down until you're at that row that corresponds with your degree of freedom in your sample. So if the degree of freedom is 22, which corresponds with a sample size of 23, or an independent sample data is 24, you have 2.07 T as your critical T. As soon as the T is then exceeding that, you have a significant difference. Okay. So why do you do hypothesis testing? Because you want to make a yes/no statement. You want to say whether hypertensive smoking men have the same cholesterol as the general population or not, or intermittent screening. So this is where a treatment effect actually significantly improves the health of a population. So here's an example of such a test, and we will discuss this a little bit more in detail. So this is, for example, this is a cluster randomized trial where basically they had health and education in school children's, where they basically tested whether intermittent screening and treatment would actually improve health and education in school children. And what was it? And in Kenya. And so this is basically one of these ways how you would report that. And we go into the details a little bit later. But basically, this is where you need hypothesis testing, because you want to make a yes/no decision. You want to know whether health was actually really improved or not. And this is a yes or no statement. This is where hypothesis testing is important. So essentially the logic here is that you have, so you know that you have a distribution of what the distribution looks like before any intervention was placed. But then you have a second distribution, and that second distribution is the distribution caused by the intervention. And this is your intervention cohort. This is the distribution you see from your cohort. So when you make such a 0-1 binary statement, yes or no, you have either the null hypothesis is true, and so you basically distinguish between a null hypothesis and an alternative hypothesis. A null hypothesis indicates that there's no difference between the two means. Alternative hypothesis indicates there's a difference between both means. So you have either the null hypothesis is true or the alternative hypothesis is true. Either or. It can only be either of these two. And now you have a possibility that your sample and your sample statistic that you're computing, and the test statistic you're computing, either gives you an indication that there is a difference between the means, or it doesn't. So now this is pretty much the same 2x2 table that we looked at with diagnostic testing. If you compare it with the cross table we did back then, we had disease positive, disease negative, test positive, test negative. And that's kind of a comparable way of looking at this. So when you have a true positive, that's the right decision to make. If you have a true negative, that's the right decision to make. If you have a false positive for the null hypothesis is essentially the null hypothesis is essentially false and the alternative hypothesis is true, but you are accepting the null hypothesis as per the test as being positive. You commit a type 2 error. That means you are not rejecting what you should have rejected. That's the type 2 error. If you are rejecting what you shouldn't have rejected, you're committing a type 1 error. So that's null hypothesis is true, but you're rejecting the null hypothesis. So the analogy is basically that. So if you have a false positive, you're diagnosing here wrongly, and with type 2 error, you're also diagnosing wrongly, and that has different ramifications. When you think about it, and we'll talk about it a little bit later, if you assume that there's a difference that is in essence not there, you would assume an intervention to be effective that is in essence not effective, right? On the other hand, if you are not seeing a difference that you should have seen, you draw a conclusion that the intervention is not effective, but maybe you have a really potent intervention and you're missing that effect, and you may waste a lot of money on conducting a trial that is essentially then shows a non-negative result. You're withholding a potentially life-saving procedure or intervention from a population. So this has ramifications, but the ramifications are different in nature. But both do have significant ramifications. So confidence intervals, we talked about it. And these alphas, these type 1 errors, are really these extremes. So you basically have 0.025 on both sides. That corresponds with a Z score of 1.96. And this is based on the standard error. And we will talk about the calculation of the set, and then it will make sense why this is now converted into the type 1 error rate. So they have different steps. So first, and I recommend this to all of you also when it comes to the final project, always make sure that you look at the actual research question that you're asking your data. And based on that, you formulate a null hypothesis and alternative hypothesis. And this helps your thinking. And is the blood pressure between diabetics and non-diabetics different? That's the research question. And your null hypothesis would be that blood pressure between diabetics and non-diabetics is not significantly different. Alternative hypothesis is it is different. And the reason why I'm emphasizing this is because it's sometimes very difficult with various research questions to really break it down to that level that you do have a null hypothesis that you actually can work with. It's sometimes because you have so many different variables, you have so many different ideas and questions that you ask or want to ask your data. Breaking it down to null hypothesis makes it very tangible and makes it very easy to digest. So I highly recommend for the analysis plan, which I believe is due on the 19th of July, to really kind of have a clear idea of what the null and the alternative hypothesis will be. So then you specify a significance level, that's in most cases 5%. Hi, how are you? Then you draw a sample size n, which usually is a consequence of your power calculation, in which you will know what sample size you will need to basically operate on an acceptable level of statistical power. And then you will have t-distribution of your samples. You will determine p-values based on that comparison. And you will compare p-values, which is essentially your leftover type 1 error risk, to the significance level alpha. And then you will make the decision whether you reject or accept the null hypothesis. So we talked about the null hypothesis. So the technical way of showing null hypothesis basically that mu equals mu zero, where mu zero. So this is a set test. This is comparing a sample mean to a population mean. Where basically you compare your sample mean, which here is labeled mu, but it should really be x bar, to your mu zero, which is your population. The reason why it's labeled as mu is because he meant to show that it's derived from the population. It's drawn from the population. And the alternative hypothesis, mu is unequal to mu zero. So an example here could be, is the blood pressure of smoking males the same as the general population? So actually should be cholesterol, not blood pressure, but there would be a numerical comparison, essentially. So you have two and one-sided hypotheses. We're not going to go too deep into that, but basically a one-sided hypothesis hypothesize about the direction of your alternative, and null hypothesis. So basically you're saying in your null hypothesis that mu is smaller equal to mu zero, and then the research hypothesis or alternative hypothesis mu is greater than mu zero. For we don't need to go too deep into this. We talked about this, and the actual calculation is now the same for a set test as for a t-test. So what you in essence do, you calculate a difference. So you have an x bar minus your population mean, that's your mu zero, and you're dividing it by the standard error of mean. So the standard error of the mean, again, this is the variability of means, of hypothetical means that were drawn from the same population. So this indicates the variability of means from samples of the same size that were drawn from the very same population, with that standard deviation that was either known from the population or was estimated based on the sample. So what you in essence do, it's like standardization. You remember where we had populations and we standardized population as per the standard deviation, and we had like 2 standard deviation captured 68% of the population. 4 standard deviation captured 95% of the population, and 3 99%. You're basically doing something comparable by calculating a difference between a distribution of your sample and the distribution of your population. You calculate a mean, a difference between means, and then you're standardizing it according to your standard error of the mean. Because the variability that you see from your sample of those sample means will be the same for the differences of the sample means to your population mean, because the population mean is a constant, right? That's just one value. So essentially, the only thing you're doing, you're standardizing those differences. So that's your comparison distribution here. And then you're standardizing it, and then you have those extreme values. And if it exceeds these extreme values of 1.96 z-score, then you're rejecting your null hypothesis. Then you actually assume the sample to be different from the population. And you can numerically quantify this, the so-called p-value, and the p-value is nothing else but the probability of you making an error by rejecting the null hypothesis. So if the p-value is smaller than your alpha, the acceptable alpha, then you will basically reject the null hypothesis. If it's greater, then hypothetically in a greater scheme of things, your population mean would still be in your 95% confidence interval, then you're not rejecting. Only if it's smaller, then it exceeded the boundaries of the 95% CI, 95% CI. Okay. So now let's go back to our cluster randomized trial. So this is now hypothesis testing in general terms. When it comes to examples like that, where we have a cluster randomized trial, you want to know whether an intervention was actually significant. And you have various ways to do that. You can have blood pressure as a continuous variable, you can have cholesterol as a continuous variable, or you can quantify risk. And this is what was done here, because you basically have here as the outcome, you have the prevalence of anemia at either 12 or 24 months. So the prevalence of anemia, so somebody is anemic or not, and there's a certain risk associated with that. That's a proportion, right? And when you have a risk ratio, you basically you have a ratio between either or, and we'll talk about risk ratio, I think, next time. A risk ratio of 1 means that you basically have the same risk in both groups. So if you have a control group and you have an intervention group, and the risk ratio is 1, the risk is identical between both groups. Now let's say if the risk ratio is greater, and that depends what you put in the numerator, usually you would put, hypothetically, you would always put the intervention group in the numerator and the control group in the denominator, because this is your referent. Your reference group always goes in the denominator. So if you're saying now that you are quantifying the risk of anemia at months 12 and 24, and you have an adjusted risk ratio, forget the adjusted for now, but you have a risk ratio of 1.03 with a 95% CI of 93 and 1.13, that basically the 95% confidence interval contains 1. That means it's not significant. So this intervention was not significantly different from the control group in terms of risk estimates. So that's what you need to take home from this. So but we'll get to risk ratio in next class. So, but concerning the questions, so the outcome variable was here a health outcome. So here was anemia. What are HO and HA is the risk in the control group the same as compared to the intervention group? And the null hypothesis would be the risk is completely the same between in both groups. Alternative shows a difference. What is the significance level alpha? If it's not mentioned, it's, well, there's a 95% CI. That means they're working with a 5% alpha. What is the p-value? The p-value is here stated at 0.621. So there's a 62.1% chance that this observation, this slight little difference, that 1.03, and which is a little greater than 1, is basically just a random chance that you have seen based on the sample, based on your sampling. Is HO rejected? It's not. Why? Because the p-value is greater than 5%. And how is this result reported? And this is where it comes down to what I showed you with how to report means with the confidence interval in a parenthesis following right after. Same here. You have adjusted risk ratio is 1.03, 95% CI. in the following from from a lower limit to upper limit with a p-value after. Although I want to make one point here, do not use minus signs. I actually think this is a very, very bad practice to do that. I would, in my papers, I would always write lower limit to upper limit, because as soon as you have a minus there, it's like, it's just, it seems like an arithmetic sign. Yes, you have a question?
So, is there any chances, because if we are taking the test group divided by the control group to have the adjusted risk to reward, like the adjusted ratio, is there any means we can have lesser than 1?
Yes, yes. If hypothetically, if you have a successful intervention, and you have, let's say that intermittent screening and treatment for malaria has a significant effect on anemia, and it improves the health outcome, then basically the numerator would show a smaller risk and would be divided by a larger denominator, which is the control group, and then it would go below 1. So everything smaller than 1 usually confers a productive effect. Everything greater than 1 is a harmful effect. Which, again, it's important to keep in mind that the 95% CI is really, that's where the money is, right? So they're seeing an effect that is as grand that that the 95% CI is basically not overlapping 1. This is essentially what you want to see. So 1.03, that it points towards a little bit of an elevated risk. I would rather, well, hypothetically with intermittent screening, no, doesn't. So this is just a random sampling error. So here you have at month 24, for example, you have a risk ratio of 1.
So this is this that's now for the issue we have to reject or we have to accept.
You would accept the null hypothesis that there's no difference. Yeah. So now let's quickly go to the example. And this is a nice example because it illustrates for a continuous variable how hypothesis testing is done. And I'm just walking you through this because we're going to have one Excel example, which is nice to see. And it's nice to do that by hand and to see it mapped out because it makes you understand the p-value really on its core. Because believe it or not, there's like a lot of people don't understand p-values, and it's really valuable to understand what the p-value actually really is. So okay, so you have another hypothesis. You have a mean cholesterol level for hypertensive men is the same of your sample, is the same as that for the general population. So you're drawing a sample of a certain size, and you're comparing this to the US population. So you have 211 milligrams per deciliter. And you want to compare this, your sample mean to the population mean of 211 milligrams per deciliter. So 100 milliliters is 1 deciliter. So the group has a different mean with the alternative hypothesis, and we're aiming for 5%. We are now drawing a sample of 25 hypertensive male smokers, and we measure the cholesterol, and we would like to know now. So we have 2 samples. So the first sample tested at an average. So these 25 hypertensive males in the first sample had an X bar of 195. And the second group had 227. So what's the conclusion? So we talked about it. X bar minus mu basically gives you the difference, and then you divide it by the standard error of the mean. So when you have 195 minus 211 divided by 46 to the square root of 25, you get to minus 1.74. So minus 1.74, if we look at the set score table, corresponds to I really got to have this table. Okay, minus 1.74 corresponds to 0.041, just like stated here on the slide. And since it's a 2-sided test, you need to multiply it by 2, because you need to account for both your alphas, and you end up with 0.082. So again, this is larger than 0.05. So again, you accept the null hypothesis. It's not significantly different. So your sample of 25 hypertensive smokers is not significantly different from that of the US population. So that's the p-value, 0.082, that's the p-value. So if you're doing this now, and this is where it's getting a little tricky. So if you're doing this now for an X bar of 227, you have 227 minus 211, that's also 16, but it's plus 16 or minus 16, which gives a little difference width, but since it's two-sided, it comes to the same result, same p-value. So since the p-value is greater, not rejected, we're not 95% confident the null hypothesis is true. What? Okay. Okay. So now we're doing a one-sided test, and the one-sided test under a one-sided hypothesis, you're only taking this once. So you're calculating here 195 minus 211, that's minus 16, divided by 46 divided by 5, that's minus 1.74. There you actually only have 4.1%, and you don't multiply it by 2 because it's one-sided. The problem is the one-sided depends on the direction that you're looking at, because if you have an alternative hypothesis that points in the other direction, and you're saying, okay, so is my mu actually smaller or equal than 211, then your research hypothesis actually points towards the sample mean being greater than 211, and that basically gives you everything above that threshold, above that set. So now you need to go in that direction. So this is directional hypothesis testing, right? So you assume the direction in which this is going, and when you have your research hypothesis, so this is your solid filled contour. So if your hypothesizing under the alternative hypothesis is greater, then you need to also take that set score and take everything above that as being your p-value. So now you're not rejecting it. So with proportions, and we briefly talked about it the last time already, we talked about calculation of the standard error of the mean. You remember, we quantified the standard error of the mean, we quantified confidence intervals for our proportions. So now you can do the same set test with proportions. You have a proportion of diabetes, so you sample 100 individuals in New York City. You get 100 individuals out, you get a proportion of 15% diabetics in your sample, and you're comparing that to the overall population of New York City, where the prevalence is 10%. So then you calculate 15 minus 10, that's 5, divided by the standard error of the mean. And the standard error of the mean is calculated like we calculated it last time as the proportion, so that's the actual percentage of individuals, multiplied by the Q. This is 1 minus that percentage, so that would be 0.9. So if we have 0.1 as the proportion in the US population or in the New York population, and we have a Q of 0.9, it's 0.1 multiplied by 0.9 divided by the sample size of your sample, which was 100 in my example. So that's how you would calculate set tests using that normal approximation that we did last time. Okay. Yeah. So if the confidence interval contains mu0, you fail to reject the null. We talked about this, and I think this is clear. One thing that is important to also keep in mind, if you have two separate cohorts and you are quantifying confidence intervals, just because these confidence intervals are overlapping, that does not mean that the hypothesis test may still not be significant. So the overlap of confidence interval is not necessarily something that means much. So that's actually a common misconception. Okay, so we talked about power. Yes. Any questions on any of the hypothesis testing? I think most of you have had exposure to that. It's nothing breaking new. But the principle is just super important to keep in mind. Okay, so let's move on to power and type 1 and type 2 error. So you have a type 1 error, we talked about it. So you have a true null hypothesis, but you're rejecting it. So you have a false positive. That is your alpha, or this is your type 1 error. This is your p-value. If you have a false null hypothesis and you are rejecting it, then you're doing the right thing. And that is your power. And that is your power that is derived from 1 minus beta. And the beta is the actual type 2 error. And that is essentially you fail to reject a correct null hypothesis. So null hypothesis should have been rejected. You're not rejecting it. And this is most likely because of too much variability in your sample, or an underestimated variability in your power calculation, or a wrong sample estimate. So power calculation essentially can help you, and we will talk about this next time. Power calculation is actually, it's quite an artful discussion and quite an artful technique, because essentially what you will need an estimate of an assumed difference. So let's assume you're planning a trial. You're planning a trial that you want to do on, I don't know, on yoga affecting blood pressure. And you're studying a certain group of people and you want to know how many people do I need to study? What is the difference that I'm expecting? So that's problem number one. It's like, how much effect is this going to take, right? So that's when you need to sit down, you need to do a systematic literature review, and you need to go through all the literature that studied yoga and the effect on blood pressure. You need to quantify what that difference, that expected difference will be, and then take this as your mean estimate. So I'm expecting a difference of 5 millimeter Hg, which is a strong claim. So now I expect a certain variability in that intervention. So now I need to estimate the variability. Again, literature review, I have all these papers. I can estimate to some extent what the variability will be. So with these things, I can then estimate what is called the effect size. Knowing that effect size, I can now go further. So knowing the alpha, what I'm willing to accept, which is 5% in most cases, and knowing a hypothetical sample size that I don't know at this point, I can basically estimate the variable of sample size. And that is sample size estimation based on power calculation. And we will talk about this next class. But basically, you can utilize these estimates, the expected estimates that you will see in your intervention, to estimate what the sample will need to be, how large the sample will need to be that you need to study to minimize your type 1 error probability.
What if we don't have enough data, enough statistics to? What if we don't have enough statistics, like trials in, for example, yoga trials?
Okay, so if you, good point. What a lot of trials do is either there's a pilot study, or there's a feasibility project where there's some data available and you can derive some estimates. What's also being increasingly often used is now in silico trials. So you start estimating it based on computer simulations. That is getting, so you will hear, so you know, in vitro, in vivo, and in silico is basically computer simulation. And you can simulate a lot of data. So you take some certain key parameters that you know from populations, and then you can estimate the evolution over time by basically running this in various simulations over time. That is one way. Another way that actually also many trials do is to have a so-called vanguard phase. A a vanguard phase. So you basically what you do is like you start a pilot study and you say, okay, so this study, my large trial is going to have that very same study design. And I utilize for the first year of the trial, this is my vanguard phase. And at the end of the year, I'm going to have a bunch of statisticians to do their work and basically give me a sample size estimate based on the data we've collected of the first year. So that's like this preceding vanguard phase. It's like a pilot project embedded in a trial. It's kind of that, yeah. So it's kind of the way to look at this. Correct, yes. And then you have new trial designs. That's I've been in a workshop lately where you have an adaptive trial design. So you're adapting your statistics as well as your sample size and recruitment and sampling based on key points, junction points that you see throughout the trial. And these are predefined not points. So, but yeah, very good question. Thank you. So, as said before, so the power should be as high as possible, because essentially alpha, that type 1 error risk that prevents the public from wrong insights. So that prevents the Medicare population to be prescribed a medication where everybody says like, oh, that's like such a great medication, but it's actually not. A type 2 error basically protects the investigator from negative studies when differences are and should be present and should be found. Not only the investigator, also funding institutions, sponsors, you name it, right? So that is disappointing results need to be understood whether they're really as disappointing as they look like, and spends a lot of money on trial participation, and it's basically withholding potentially very important insights and effects that should have been found. If we fail to reject the null hypothesis, the probability that the null hypothesis is true equal to 1 minus alpha. No, it's not, because you still don't know about the variability. It is still a probability. So the type 2 error is still the power, but still underlying variability and sampling variability. Statistical significance versus practical significance, that is important, because when the n increases, you will be more likely to have significant results. So if you study a lot of patients or a lot of individuals, you're very likely to see a significant p-value. And that's a problem, because that doesn't necessarily mean it's really practically useful. Because if you see in a large population of 200,000 patients a change in blood pressure by 0.01, this doesn't mean the world. This means virtually nothing. So that's just because the variability got so small, because it's such a large sample that you're essentially reporting something that is not practically significant. So that distinction is very important. Okay, so that was the first part of it. Any questions on any of this? I think it was simple, right? So I think it's quite logical. And so now next, I want to briefly talk about hypothesis testing for 2 sample means. And that essentially, these are the most commonly done tests. So the set test is rather a rarity. But these 2 sample t-tests are really the most commonly used tests. So again, keep in mind, set test and t-test, the most important thing is that with the set test, you either have a very large sample where the set score of 1.96 indicates an alpha of 5%. So that's at 500, it's identical. After 30, you kind of get away with it. Or alternatively, you know the true standard deviation. You know what the variability in the population really is, which is a rarity. When you have now a t-distribution, you're estimating the variability in the population based on the variability in your sample, and you're changing the division of the sum of squares to derive the variance. You're changing that to not divided by the sample size, but by the degrees of freedom, which is n minus 1. So The t-distribution equally allows the computation of confidence intervals. What is important to keep in mind, when you have two independent cohorts and you're comparing two different cohorts and two different distributions, you have a dependent and an independent sample. What does that mean? Dependent is you have the same individual during two conditions. So you have a before and after condition. So the individual walks along and you follow and you collect the data from two different time points. Independent samples are two independent subject groups. These are two entirely independent cohorts that have nothing to do with each other. And that's really what you want to have also in a randomized controlled trial. So essentially you want to have entirely different individuals that are entirely identical in terms of the distribution. That's what you want to create. That's why you're randomizing at the end of the day, because you want to minimize confounding.
1,000 patients.
Yeah.
Same indication. They have the same indication, same disease, and like from the same age.
Yeah.
But like female and male, and we want to randomize them into the identical groups. I mean, what if we separate females and males, and then I mean,
so
we want to mix them, right?
Yeah.
We want still identical two groups.
Yeah.
Into two groups. How to do this?
Well, you randomize each participant in either group. You randomize whether he's going to be in that group or in that group, and that's like the sampling we did, for example, right? In the AIMS data.
We don't want to know how we are. Like, we don't know if patient would get placebo or treatment, right?
Correct.
So in this case, how we should do.
Well, you would so randomization is something that can quickly be programmed, right? So that's a programming algorithm, and you can tell the program how to randomize. So we have done this, for example, with binomial data, with binary data. You can use a randomization scheme like that. Randomization, you're probably going to talk about this in the other class, how to randomize. You can randomize on strata, you can randomize on biological sexes, you can randomize on facilities if they're coming from different facilities. You can randomize on different contributing sites. So there are different ways to randomize. Practically, it's simply done with a randomization scheme on a computer that can quickly be done. You usually would do this right at the beginning of the study, and then just each participant comes in from a respective site. You would usually have, so you have the contributing site and you have the data coordinating center, the DCC, and the coordinating site enters in trial master or whatsoever, enters, okay, so we recruited now Mr. Smith. And the response from trial master from the DCC is then whether the individual is in that group or in that group. So they are doing this on the back end, but they are randomizing it on a site level.
Yeah.
But
I think like maybe they at the start they may just separate female male the groups, and then like also separate the treatments, like 50 placebo, for example, 50 treatment. And then each of the group we have that now we have the treatment and equal treatment and placebo quantity together 100, and we will give it to 100 female, so that we have anyways we will have 50-50.
What's the advantage that you see?
What?
What's the advantage of doing that?
In order to at the end of the study we have like similar groups, females and males in the randomized groups.
But you would have that anyways.
The quantity, I mean.
Yeah, but in terms of quantity, you so do you necessarily know that the quantity that there's a 50% ratio, there's 50-50 in each group? You don't know that.
Yeah.
Yeah. Yeah.
500, and we want 500 from there and 500 now.
So the beauty in no, I understand what you mean, but then you're restricting your randomization to an exact 50-50 ratio, male and female,
Yeah.
which may not necessarily be correct. Because if you look at a population, it's like, so you may have here in Gramercy, I think that's Gramercy. Here in Gramercy, you may have a different gender distribution than you have in, I don't know, on the Upper West Side, on the Upper East Side, or on the Lower East Side. So you want a representation of the population, right? Yeah. So if you're restricting that to 50%, you may be introducing a confounder you don't want to have.
So like exactly very identical groups is not that necessary.
It's rarely correct.
Yeah.
So it's
identical, not that important.
no, because no, identically, you don't, in the end of the day, you don't really care about the distribution, right? You just want a representation of the respective site. Because analytically, you would then probably take site into account when you adjust your results, for example. You would adjust for the recruitment side. And if you see a different gender distribution in one of the sites, that would probably give you a signal in terms of adjustment.
Yeah, so you can, by time, adjust recruit more patients.
Correct, yes. So you would really only stratify your randomization according to clusters. And these clusters are usually, while you can make a cluster randomized trial, that's start number one, which you will certainly discuss in the other class. So that's one thing, but these clusters need to be very carefully selected and defined. Usually it's something geographically, something culture, something, I don't know, whatever the constraints could be that distinguish one side from another side or one cluster from another cluster. Something that is inherently making a difference. Gender is, in the end of the day, just a proportion, right? Yeah. No, because it's, so you would see, for example, for a blood pressure drug.
This is right. We have mortality rate for cardiovascular disease higher in men compared to female. So
yeah, careful. Oh, but that risk advantage, you women lose that risk advantage at one point in your life, right? Yeah. And after, what's the average age of menopause is like 60, 62, 63. After that risk is identical.
Yeah.
So that goes away, right? But now if you are basing it, if you're taking this into account and you're saying, okay, so I want equal gender distribution now, you're not taking care, you're not taking that into account. Yeah. Because if you just no, because that's you're just filtering it down on a whole different level, and then you get a different confounder in, which breaks you down on a whole different end. So it's not as simple. So you really want, on a participant level, you want an accurate representation of the population. So you want to sample as randomly as possible, and you want to randomize as general as possible. Because in the end of the day, what you really want, you want an absolutely identical control group and intervention group. Because things like that, for example, that the risk just aligns with that of male participants after the age of 60, 70 or whatever, that is a confounder which is virtually impossible to account for, because you don't have this data. And you don't know whether, I don't know, Miss O had her menopause was 57 or had it was 68. You don't know these things. And by having equipoise, and that's the technical term of this exchangeability between both groups, having that basically takes this out as a confounder. But the excellent question is a good conversation, please. Thank you. All right. Okay, so we have paired and dependent samples before and after situation, and that's actually that's the cleanest way of approaching this. When the individual serves as his or her own control, because then you know that Miss Smith at 57 to the age of 58 had that change in blood pressure. So that's the purest form of analysis, but it's just then you have different confounders coming in and different problems coming in. And then you have independent samples. So there are examples of paired and dependent measurements, but I think it's quite logical, right? It's like everything that basically has a time point and moves forward along a certain time trajectory is basically paired to be seen if it's the same individual. If it's different individuals, then it's independent sample t-test. Okay, there is one major difference, and that is really important. So with a z-score or with a t-score computation, you basically have the x bar minus your population mean, and you're dividing by the standard error of the mean. So with paired samples, your comparison distribution is not an assessment at one time point, it's the difference between both time points. And that makes the paired sample t-test tremendously different from an independent sample t-test, analytically and also in terms of inferences. So it's really this D bar that you're comparing. That's your comparison distribution. So also for your paired sample. So you would do the same, you calculate the difference, and then you quantify the variability of your differences. So it's actually the variability of the differences that you quantify.
Even the example here.
Of a paired t-test?
Yeah,
no, I understand. Classical example is like, okay, so you have a class, you have quiz 1 versus quiz 2. So students were subject of intensive tutoring between both tests. And then you see the change from quiz 1 to quiz 2. And then you could randomize students into either group, right? And you could basically take these differences and also do an independent sample t-test. But basically, just compare it from quiz 1 to quiz 2. That could be analyzed as a difference between those two tests. That would be the simplest example it could be. Or here we have birth weight here. Average heights of males and females at age 7 to age 10. Anxiety levels of individuals before and after an intervention or after meditation. Something along these lines, right? Okay, so the example here is an independent sample t-test. Does cell phone use while driving impair reaction times? So students used a machine that simulated driving situations at irregular periods. A target flashed red or green. Participants were instructed to press a brake button as soon as possible when they detected the red light. For each subject that the experiment analyzed a mean response, 32 students were randomly assigned to the cell phone group and 32 to the control group. So that's the independent samples t-test. So now this is the outcome. So we have here, again, box whisker plot, we have the response time, and we see with cell phone use, there's a substantially higher reaction time or longer reaction time, and the asterisk indicate they're also significantly different from each other. So we're seeing the difference here also reflected in X1 and X2. The difference is here when you're quantifying the standard error of the mean. Okay, I don't want to go too deep into this, but basically you need to calculate a pooled variability of both cohorts. So you need a pooled standard deviation and a pooled variance, and that allows you to do, excuse me, the comparison. But I'm not going too deep into this. That pooled standard deviation is basically this one, where you have two different standard deviations, and you're basically creating aliquots weighted as per the number of participants in each group. That's all you need to know about it. You can either pool it or not pool it. There are different ways to do the pooling. Wilks test that we will do in R is the most common one. Yeah, we're not doing this. Yeah. We're not going too deep into this. This is not necessary, but basically you get, as the outcome, you get a test statistic, you get a t-score, you get a degree of freedom that you know from, and you get p-value. That p-value basically gives you the type 1 error rate. So since the p-value is smaller than 5%, we're rejecting the null hypothesis, and we say they are significantly different. A cell phone while driving is not a good idea. Now you do a dependent sample t-test. So you basically have one group that use cell phone, and then they basically drove the same thing with no cell phone, or did the reaction test without a cell phone, and they were tested again. So now we're focusing on the difference. Using cell phone, yes, no, and we're quantifying the difference of these 32 individuals. And then we're using a paired samples t-test. Okay, that's paired sample t-test. Here we have test statistics between those both. The degrees of freedom here are 32 in the group, -1 is 31. And we're seeing there's again a significant difference. So you're testing within the individual, you're quantifying the differences, and the differences becomes a degree of freedom. So it's not the two groups anymore, it's only the degree of freedom of the differences. Yeah. Okay, so we talked about this. So we have paired samples, independent samples with continuous and proportions. You can calculate the differences between the proportions with normal approximations, and you can compare them, basically the differences between the paired observations and paired sample, and you calculate differences between means, and you are characterizing it using a pooled standard deviation or non-pooled, but most likely it's pooled. This is basically all theory that we had for today. Now we can spend the rest of the time on R. Are there any questions? I think it's fairly simple, and it's just important to kind of have reviewed just a thing. Yeah, so there are limitations. So we talked about statistically significant doesn't necessarily indicate practical significance. Secondly, a p-value cannot be interpreted as the probability that the null hypothesis is indeed true. It just gives you a probability of you rejecting something that you shouldn't have rejected. The 5% is kind of a debated value. For your large samples, I would likely go for a smaller threshold. So you can design this as a 1% alpha or 0.5 alpha, hypothetically, if you wanted to. So particularly with large sample size, this really becomes a problem. You cannot make inferences for an individual based on your insights of the population. So if you see no significant difference on a population comparison between two sample population, that doesn't mean it's not effective in particular individuals. That's usually subset analysis and sensitivity analysis, where you may still find some signals. The sample size is not necessarily an obstacle on drawing inferences from your studies. Just because a sample size is large doesn't necessarily mean it's true. We're dealing with probabilities at this point, so there are still possibilities of errors, right? Study design is extremely important. This can be statistically significant by chance, particularly if you do multiple comparisons. And we will talk about analysis of variance. If you have multiple comparisons, you may find significant differences just by random chance. And that is, unfortunately, in our times, with a lot of analysis being done, you find data on various aspects. So if you look for specific insights in one direction and you go on Google, you may find all the studies claiming that one side. If you then Google studies that point in the other direction, you find those studies as well. And this is where the power of meta-analysis becomes really, really central. So nowadays, when you go in the level of evidence, you have as the highest reference, you have a randomized controlled trial. This is the most important thing to essentially study, that you have a randomized setting and you create solid inferences based on data that was prospectively designed, and with randomization, confounding was minimized to the maximum level. But what nowadays, with this enormous amount of studies and data that's being published, what becomes more and more important is really meta-analysis. And meta-analysis that not only analyze the mean estimates over several studies, but also assess the risk of bias. And the risk of bias is like, I did a meta-analysis, I worked now, it's now under review right now, but I worked 2.5 years on a meta-analysis with a group of people, an international group of researchers. And the risk of bias in studies that are being published in high impact journals, you wouldn't believe it. It's incredible. The reporting standards have improved now, but they have been really, really low over decades. So it's definitely, but there's increased awareness nowadays that this has become better and better. But yeah, bias and bias definitely quite frequently seen. And that feeds into that statistical significance can be seen just by chance without any real underlying biological plausibility. Publication biases also need to be being paid attention to. So publication bias is basically that something is more likely to be published when it's actually significant and it shows an actual effect, which is a problem on its own right. And there are ways how to analytically approach that in the context of meta-analysis, quite frequently done. But basically, you need to pay attention and you need to understand the true effects that are being reported are not necessarily the effects that you will be seeing in a population. And this is where real-world evidence, again, becomes extremely important. But yeah, so this is all on hypothesis testing for today. Any questions? Yeah.
For journals, there are some impact factors rating, right?
Yeah.
So does it involve statistical analysis of what they are going to print on their journal publish?
Say this again, please.
Yeah. So does impact high
impact factor, yeah.
Higher trust with this qualification.
Yeah.
Yes.
So there's a common consensus that impact factor reflects something. Does it necessarily reflect as much as some claim it does? Not necessarily. Particularly now in our times and ages with absolute information and various possibilities to promote journals and articles. And the impact factor has become quite criticized. So you had a shift in impact factor and you had a tremendous increase in impact factor. And much of this is also associated, I hate to say that bluntly, but there is, you can influence it. And so I have heard opinions that it is being influenced by the editorial boards for good reasons, by the actual publishers, because the higher the impact factor, the more prestigious the journal becomes, the more often it's being cited. So the impact factor, I'm not an expert on the impact factor, but it's basically, it's put together of various components, and it mainly has to do with how much is being cited versus how often are articles from a particular journal being cited.
But being published there, it's like they should
It is
have good results, right?
it is commonly accepted that it is better that you publish in a high impact journal. Yes. There are essentially, in an academic settings, there are universities that actually would only count publications towards some certain merits if it was published in a journal with a certain impact factor threshold that were of a certain impact factor. So yeah, it's still a common metric that is being used. I think the controversial part is just, is it still the best metric, right? So it's not only on an impact factor, it's also each individual. Once you become a researcher, you have your own metric. You have the so-called H index. H like the letter H, which is basically the number of publications in accounting for the number of times you've been cited. And so this on an individual level, that's quite frequent. And yeah, I guess we live in a time where everything gets a metric, right?
Yeah. Just curious if they have some, this journal have some data analytics specialists.
Oh, they do.
Like all of this data.
Oh, they do.
Yeah. And say like, we will not publish this because it is, we don't think that it's sufficient for a journal to publish your study, for example.
Oh, that will certainly happen, yes. So usually these decisions are made by an editorial board, and the editor-in-chief and the editorial board usually guides the direction of the journal. So they will decide which direction a journal is headed to, with their focus on how many articles of that kind, how many articles of that kind. So there is a certain level of arbitrary choice involved. But it's also, it's kind of a weight on a particular area. So, you know, in my world, I know the journals that are more likely to publish epidemiological studies versus those that are more likely to publish meta-analysis versus those that are more likely to publish clinical studies. So you kind of, as a researcher, you kind of learn the focus of the journal, and you kind of know which journals it's a good target for your work. So yeah, but it's not only the impact factor. It's really, there's a lot of associated other factors involved in that. Also, many journals do have an entire association behind them.
Yeah.
So that means if you have, I don't know, if the American Society of Epidemiology publishes something, so there is more than the impact factor alone that counts. And so, yeah. So it's not that easy to break it down to just one metric. Okay, so we're going to do a little bit of programming. So we have now Practice Lab 6 today. And Practice Lab 6 is basically, what is it? We have, so Practice Lab 6, we're doing in Practice Lab 6 essentially an exercise that I also do with my undergrads, and I just thought it would be a nice exercise. You don't have to do this for the graded lab. I just want to walk you through that. So this is now, so there are 729 and 730. So basically this is conducting, and this comes down to the most commonly undergrad examples, right? So it's the SAT test. So it's basically comparing a sample of 50 people that scored on 542, and you compare it to a population mean of 500, where the standard deviation is known to be 100. And I'd rather show you in Excel, so the Excel spreadsheet is also on it. And we're also going to do, for the sake of time, we're only going to do 729 because 730 is kind of comparable. So, but when you go through the steps here, so you basically you have a sigma, which is your population standard deviation. Then you have your mu, which is your population mean. Then you have X bar, that's your sample of 50. So the first step, what you're going to do is you calculate your standard error of the mean. So this is here, nothing else but your sigma divided by the square root of your n. That's 14. Then you, in step 2, you basically design your null and alternative hypothesis. You're basically defining your alpha at 5%. And then you quantify your set, which is 1.96. And you have here your lower and upper limit CI of your sample, notably. So that's 542 plus minus your margin of error. So that's the upper limit. So you know already when you look here at lower and upper limit, you know already this is statistically significantly different from your population mean. So, but how do you calculate this now? So when you go now and calculate your set is calculated as your X bar minus the mu divided by your standard error of the mean. That gets you a set of 2.96. And if you go on the set score table, 2.96 is, so let's look for 2 minus 2.96 because that gives us the rest on the, so gives us the actual tail to the left, right? And we know it's by symmetric, so it's the same size. So it's minus 2.96, that's like 0.015. So this is essentially your p-value if you multiply it by 2. So you do 0.0015 multiplied by 2. So now you have your p-value as being 0.3%. Consequently, you're rejecting your null hypothesis. Good. Easy. So now if you have X bar, you're hypothesizing that X bar is greater equal than mu. So that's your null hypothesis. Your X bar smaller than mu is your alternative hypothesis. So now think of that normal distribution. So you're thinking now it's greater, and you know it is, right? 542 is greater than 500. So you have now 2.96 as your set score. You're using 1 times p because it's a directional, you only take one tail, and that tail is 0.9985. This is greater than 5%. This is when you accept your null hypothesis because your null hypothesis is true. Equally, if you say, okay, so this is now a right-tailed hypothesis, so you have an X bar is smaller equal than mu, that's your null hypothesis, which we know it's not. Your research hypothesis X bar is greater than mu, which we know it is. You basically get your set of 2.96. Then again, it's 0.0015. So that's the way you need to look at this. And this is, I just want to kind of illustrate what we looked at before in numeric terms. So this is how you have to break this down. And now the R code, are there any questions to this? I think it's kind of logical, like keep in mind that what we looked at before with the hypertensive smokers, it's essentially this comparison. This is our 2.96, that's the 0.015. So that's the rest error risk. And this is if we have the null hypothesis that the mu is actually larger. So this is no smaller. So that's now when the null hypothesis is more likely to be correct. So this is the illustration in an SAT example. And I just wanted to show you that. Okay, so we have now in part 1, we have now this calculation here in R, and you will see here, you get with P norm set. This is the way how you can get the actual P value under your null hypothesis. So this is how you quantify the percentage of a particular set score. So this function P norm and the set score is basically your set score table. So whatever set score you want to have from the table, you just put it in P norm and it will give you the respective proportion. So these are just the same examples. Basically, this is the 0.0015. This is the calculation of the confidence interval, which we have done already. So I'm not going to go much through this. This is the calculation of the effect size. Effect size is calculated by x bar minus mu divided by the standard deviation now, and not the standard error of the mean, because the effect size basically takes the sample size out of the equation and gives you an estimate of the difference and how much that actually weighs in the greater scheme of things minus the sample size. So because the standard error of the mean is sample size dependent, is dependent on standard deviation divided by the square root of the sample size. Therefore, a higher sample size will lower the standard error of the mean. If you're now taking that calculation out and you use the actual standard deviation, you get the effect size. And as per Cohen, he quantified the effect sizes as being more reliably showing the actual effect. And this is, as per the conventions of Cohen, this is medium size effect size. Good. Same example. So this is 730. 730 was the same example, just with different numbers. We don't need to go through this. So let's just click through all of this. But let's go now to part 2. So part 2 has a little bit of peculiarity, which we haven't touched on before. And I would like for you to please do an exercise with me, because so on the Canvas module, you have today under assignments a data set. Please download this data set in the BTM6000 folder and put them in the respective folder of this module. Reason for that is because we're going to import this data now into R. And we haven't done that so far. Right now, we've only queried it and gotten it from online, which made life a little easier. But now I think we're at this point that we need to deal with that. Okay, if you click now, so there's going to be who's on Mac, who's on Windows. All Windows, everybody Windows, Mac. Okay, so
No way.
okay,
Professor,
in Windows, yeah.
Can I ask you something? I tried to download this as, I tried to import this as read.csv.
Yeah.
Was it okay?
Yes, that's perfectly okay. Yeah. Did you use it with the codes that I showed here?
Yes. Enhanced test dataset.csv.
Yes, that's perfect.
Okay,
That's perfect. So we need to adapt now line 93 to 96. So, and the way we're doing that, we're copying now that file into that folder. And okay. So we're copying that, oh, the electric outlet on the one. So we're copying now our file in that folder, and then we make a right click on it. Once we make a right click on that, all the Windows users should have something that is called properties. And in properties, you find the folder name. For the Windows users, this should be something like C:\\, etc., etc. Is that correct? I cannot show it because I'm here on a, wait, I could show it here. I don't know. Yeah, exactly. Location. We need the location. If we go here in a file like this, we make a right click, we go on properties. So here is now location. That location, please copy over into your RStudio. And by doing that, you can now enter it into input and output folder. Do you see that? Target location. Can I make a right click on? Yeah, location. Yeah, so that's your input folder. You just copy this into RStudio. You're okay, Natalia?
Yeah, my computer's being weird. Trying to find the source.
Okay. Oh, okay.
Or you're making shortcuts, right?
No, I'm not. I'm actually just copying the folder structure, the folder name.
Okay.
That's simple. You got this. Yeah, it's just copying it. You got this. I'm positive. Okay, how do others?
Like, where should we copy the?
So you put this in line 93. There's input folder and output folder. Whatever is written there from my folder structure, please overwrite. The only thing I will need to ask you is to, oh well. Listen. The only thing that is necessary to do when you copy this all over, it's important that you transform all the backslashes. You need to transform to slashes. Yeah, because this is Unix-based language. You will not be able to use a backslash. That's a Windows thing. I don't know when they came up with that, but so override all the backslashes with slashes and make sure that you have after module 6 a slash. Okay. And label input folder and output folder both the same.
What did you say?
Input folder and output folder should be the same. Excuse me, there's some water out there, but yeah. Okay, we got this. Okay. So once you got this, please go on line 91, line 93, line 94, and then input folder and output folder should look approximately something like it looks here. It should be like something like C:/ not backslash, then your username / desktop. So all the backslashes need to be slashes, and then there need to be a slash after module 6. If you have done that correctly, and you have that enhanced test data set in that folder that you're currently targeting, you should be able to just load this data set. This data set are 200 individuals from the enhanced data set that basically we can look at now specifically. So if we're clicking now into the file, what we see now, and that's one thing that R does, which is super annoying, that it keeps on doing that. It enters, when you import a CSV file. A CSV file is a comma-separated file. It's not an Excel file. It's basically a file. It's a text file. A text file which has numerous entries, each one for each variable, which is separated by a comma. That's why it's called comma separated values file, CSV. And so R will then automatically recognize which is a name for a variable, which is an actual entry. And R does something which is super annoying, which is it leaves the first column that is kind of a running number, which is something you don't have to deal with. It's just from 1 to 200. It's useless. But line 99 basically removes this column. And it does that by basically just reducing df to 2 to length of df. So basically it's just reducing that one. So with summary, we then see what this data looks like. So we have a couple of interesting parameters there from the main enhanced data set. I also meant to inspire you for your final project already a little bit. So we're having age, gender, or biological sex, height, weight, diabetes, SPP, DPP, physical activity, marital status, and male sex as a factor. So now in the following line, 101 to 104 creates now factor variables for all of these. And that's basically where you see male sex factor stratified in 101 males, 101 females, and 99 males. You wanted to work with 50%, right? Okay. Then we have marital status, basically broken down in divorced, lives with a partner, married, never married, separated, or widowed. Then we have diabetes as a factor, was either having diabetes or having no diabetes. We have physically active and physical activity as a factor, either no or yes. No quantitative term, but there's a quantitative variable in there too, in the enhanced data set. So now here we're doing something that I have mentioned before that we did already. So this is data frame where we're kicking out all the NAs. So that's another way how to deal with NAs. That's removing all NA variables. That's line 106, where we're basically removing all NAs. Then line 107 removes all that are younger than 19 years old. So only those that are older than 18 will be in there. Kicks out another 40 or 39. So now we have a summary of height and weight on line 108 and 109. That's just giving us a central tendency, a little bit of an idea of how the data distributes, min and max values. Okay, and then we're calculating line 110, and that may also be interesting for you for the final project. We're calculating body mass index. So body mass index, I hope all of you are somewhat familiar with that as a parameter. So it's basically, it is the weight in kilograms divided by the height in meters square. It is generally, it's inaccurate and not overly representative or in any way biologically plausible parameter, but it's commonly accepted as being a way to kind of reflect body composition. It distributes usually somewhere between 16 to 33. Not true. That's where the bulk of the data is. Somewhere between 16 and 33, I would say, is the majority of data points. If we're doing this here, in our data, it's 25 to 33. So we have a rather bigger crowd. Okay. So as per the WHO criteria, everything smaller than 18.5 is considered to be malnourished or kind of undernourished. Malnourished is maybe a little too extreme. 18.5 to 20 is, I forgot the proper term, but 20 to 25 is kind of normal. 25 to 30 is considered overweight. 30 to 35 is considered obese. Everything greater than 35 is, yeah. I forget the exact term. But definitely also obese. Okay, so now we want to test the representativeness of systolic blood pressure to the overall population. Under the assumption that the normal population is 120. So we know our mu to be 120. So now mu 120, sigma is the standard deviation because we're estimating it. X bar is the mean of DF-SBB in our sample, which is 124.5. N is the length of our sample, which is 139 at this point. And the standard error of the mean is here 1.7. You see this all calculated here on the right. With each of those lines, we're calculating each of these parameters. So now calculating a set gives us here a set of 2.7, which we know is greater than 1.96. So therefore, we have a significantly different sample as compared to the population mean. So that's the one-tailed test. So now we want the p-value that can be calculated with line 123 and 124. It's basically again using the p-norm function, and it gives us a p-value of 0.007. So that's substantially less than 5%, right? Excuse me? Excuse me? Yeah, what value? 0. Oh, the C?
Yeah.
Oh, yours is 0. I don't know, you probably may have missed a step. Just try to start again with mu equals 120 and go all these steps down. It must be somewhere in the earlier steps. It shouldn't be 0. Okay, line 100. Yes.
Professor, I tried to paste these values for sigma, X bar, and standard error of mean on console. But I wasn't really able to round it off. Could you please tell us how to do that?
Rounding it is quite simple.
Yeah, like
If you want to round, so let's look at standard error of the mean. So this is 1.682158, right? So if you want to round this, you just do round, parentheses, comma, so SEM, comma, and then give the number of decimals you want to show. So if you do comma 2, it will only show 2 decimals.
Yes, but how can I do it if I want to do it for all of these values altogether?
For all of these values altogether, which values do you mean?
Sigma, X bar, and SEM.
Well, you can do it like this, for example. You can do round mean DF-SBB 3, assigns only 3 decimals to that particular value. Is that what you mean? Did you see it change now here?
Yes, I mean, I was just wondering, can we paste these values on console in rounded off fashion?
I'm still not sure I understand what you want to do now. So here you have the environment. So there's an object that has a certain number assigned to it, right?
Yes.
And if you want to start this in the console, you can start this quite easily. You can display this quite easily with rounding or no rounding.
I was trying to do this in one line.
To do this, this is being rounding sigma and X bar to only one parameter, or to only 2 decimals. Is that what you mean?
Okay. No.
No.
Like on the console, I tried to paste it, and in R I wrote paste, and then in brackets sigma, comma, x bar, comma, SEM,
You mean
comma,
something like this. With X
SEP.
bar, paste X bar, sigma,
Right.
like this.
Yes. So I was trying to round it off, but
Round
how can I?
like this. How about that?
Okay. Okay.
Yeah.
Yes. Thank you.
Okay, good. You're welcome. Okay, so let's quickly carry on. So we have here 127 gives us now a DF1, which is basically a subset of our DF, which contains only married and divorced individuals. So we have now a summary of systolic blood pressure of married and divorced. So we see that blood pressure seems to be increasing when you're married. So we want to now change the factor, and now we want to compare whether well, actually the blood pressure goes down after you're divorced. So you basically compare now these two against each other. So if you do t-test, oh, that's fine. Oops, there's a little mistake. Please correct that. We need in t-test, in the t-test formula, we need to add now the second vector. So this became a one sample t-test. Okay, so you need to change now, please add the second vector. So you have DF-SBB divorced and DF-SBB of married individuals. That was line 131. Needs to be added. So it ended with this comma here. And you need to add just this second vector here for married people. So t-dot test exactly answers for an x value and a y value. So the mean of x is here divorced. That's DF-SBB for those that are divorced. And you have DF-SBB for those that are married. So that's mean of y. So you need an x and a y, and then it will automatically compare these two distributions. And that's what it did here. And here, test one. So I'm packing this t-test now into test one. And test one, if I start this, gives us this two sample t-test. So we have here divorced and married. That's the formula. Here we have a t-score of minus 2.7. We have a degree of freedom of 10.32 with p-value of 0.8. So it's actually only an urban legend that your blood pressure goes down when you're divorced. It actually is not significantly different. So you basically also see this corroborated with your 95% confidence interval. We have minus 19 to plus 15, contains the zero, therefore is not significant. Good. So that's how you use a t-test. In case you have paired data, the only thing you need to do here is to add the function paired equals true. That gives you a paired t-test. So that would be a paired t-test now, but we don't have the same length. So I'm letting this go now. So this gives you an independent sample t-test. Now we have box plot of both of these blood pressures. So that's the box plot showing blood pressures in divorced and married individuals. So now we have lastly, and that's the last 4 minutes. Now we have write.csv. That is writing now the object df again as a CSV file into that very same folder, but this time it's the output folder. This is why it's important to define input and output folder, because now you can utilize these in the paste function. And in the paste function, you're telling here that this is enhance test dataset subset.csv. Actually, that should be df1. Sorry for that. So write.csv, df1, paste output folder, enhance test dataset subset.csv. That is what you want to do, and this is what you run. And the outcome will be an additional data set, which is this subset data set created here. That is only our divorced and married people only. Okay. All right. Any questions? Good. Created lab 2 is super simple. Is essentially asking for nothing different than creating again a subset, computing descriptive statistics for all variables of the full subset, compare the BMI between diabetic and non-diabetic participants. Depict the data of BMI in a box whisker plot, separating both diabetics and non-diabetics, and then put it all in a markdown HTML file, just like last time. Okay? That is created lab 2, yes. But it's just due next week. All right. If no questions, we can conclude for today. Any questions on Zoom? All right. Then thank you so much. Have a nice evening, and I'll see you next week on Wednesday.
Thank you, Professor.
Thank you. Bye, everybody now.